UniFi access points have a very useful feature. It's called bandwidth profile. You can use it to limit the download and upload speed. But in real world usage, people have many misunderstandings about how to use it, and it also has some counterintuitive behaviors. In the video, let's first talk about several examples, then let's dig into the system to understand how UniFi's bandwidth profile works from backend. Then we can understand why the strange behaviors exist. This is the lab environment for this video. I use a UDM Pro as the router connected with a small PoE switch, and the PoE switch will power two separate access points, U6 Lite. From Wi-Fi client perspective, I'm using 3 physical computers, a PC running Linux, and 2 Mac machines. For the PC, I will either connect to the first AP or the second AP. For the 2 Macs, they are both connected to the second AP. By the way, this video applies to whatever UniFi router, switch, or access points you use. I just happen to use these devices in this video. And in the UniFi controller, I set up 3 different bandwidth profiles. I give them a little bit strange upload and download speed, just make it easier for us to identify the settings in backend later. When it comes to Wi-Fi SSID, I have 2 set up, and if you check the Z11, it's only used by AP2. Scroll down, it will use the 11 bandwidth profile. For the other Wi-Fi SSID, Z99 is only applied to the first AP. It used the 99 bandwidth profile. Let's go back to the diagram. You can see I also list the information here for the 2 AP. What are their SSIDs and what are the default bandwidth profile. And for the 3 computers, sometimes I use the default bandwidth profile, sometimes I use the customized one. We will talk about the details later in the video. Now let's talk about several things that people either get confused or have some misunderstandings. First problem, why the bandwidth profile only applies to wireless client. On the screen, you see the current situation for my network controller. There are totally 4 devices connected. 3 of them are through Wi-Fi. 1 is wired from Ethernet cable. If you pick a Wi-Fi client and go to settings, in the bandwidth profile, you have options. You either choose the default one, which means whatever SSID you connect to, you will use that SSID's default bandwidth profile, or you can choose from the available customized ones. I have 4 of them. That makes sense. That's what people expected. But if you go to the wired client, go to setting, you don't see those options. This is a common complaint. People will think, okay, why not extend this very useful feature to wired client, right? And people may think it's simply a stupid user interface limitation. No, it's not the case. Later in the video, you can see once we dig into the system, the way Ubiquiti implement the bandwidth profile, it can only work for wireless clients. For wired client, there are several different ways to limit the bandwidth. I may have a separate video in the future, but in this video, we will not talk about how to limit the bandwidth for wired client. Second problem, the bandwidth profile applies to all the clients for one given AP, or it's applied to each client individually. So let's say in your system, you have AP, you give it a bandwidth profile. You may expect, okay, it doesn't matter how many Wi-Fi devices are connected to your AP, you expect they share the same bandwidth. So their total download and upload speed shouldn't exceed what you said for the AP, right? That may be your expectation, but it simply doesn't work that way. Let me do a short demo of this. I'm going to use these 2 Mac machines, connect to this PC to test the upload throughput. As you can see, the PC, I will connect it to the first AP. From the PC, let me run 2 iPerf3 servers. In the PC side, I launched 2 terminals. For each one, I'm going to run 1 iPerf3 server. Each one listens to different port number. In this screen layout, I will show you the two Mac machines terminal side by side. I will run iPerf3 clients so we can see what's the overall upload speed. From the network controller, you can see the two Macs, they're connected to a second AP with SSID 11. PC is connected to the first AP. Bandwidth profile is 99. For the two Macs, their upload bandwidth limit is 1.1 megabits individually. From the two Mac machines, let me launch the iPerf3 clients. For the first one, connect it to the PC and connect to the first port. As expected, the average speed is lower than 1.1, right? Yeah, you may see it's fluctuating because it's Wi-Fi and my computer is far away from the AP, so it won't get the optimal speed, but it doesn't matter. It doesn't really impact what I want to show you. Let's move on to the second Mac machine. I will connect to the second iPerf3 server in the PC side. If we check the two side by side, you can see the overall speed in total exceeds 1 megabits for sure. Sometimes it's close to 2 megabits. But the two Mac computers, they are both connected to the same AP, and the same AP has the 1.1 upload speed limit. So if the speed limit applies to the whole AP instead of individual device, it shouldn't happen, right? Bandwidth profile applies to client instead of AP. Even if you don't customize the client's individual bandwidth, even you leave the setting as default, the same thing will happen. Okay, that's the second problem. We will explain the technical reasons later. Move on to the third problem. We just tested if the PC is connected to AP1 and the two Macs connect to AP2. For each Mac, which is a Wi-Fi client, the bandwidth profile applies and we can see the effect, right? But what if we move the PC to the same AP as the Mac computers? Whether the bandwidth profile still work? That's the third problem I will show you. In the left side, you can see I already connect the PC to Z11 SSID, which is only available in the second AP. So now all the three computers are on the same AP, and I already made sure for all three of them, they don't have any customized setting in the bandwidth profile. They all defer to the WLAN's bandwidth profile, which is upload 1.1 megabits. So let's see whether it's the case. From the Mac number 2, let me use iPerf3 to do a upload testing. Let's see what's the throughput. See the result is much more than the 1.1 megabits which we set in the bandwidth profile. Then let's see what about download. Let me use the -r parameter. You see almost the same speed as upload. Remember, in the bandwidth profile, we set the download limit to 11 megabits, right? So this number is also much higher than that one. Both download and upload, the limits don't work. Why it happens? Because both the server, which is PC, and client, which is Mac number 2, they are on the same AP. In this case, the bandwidth profile is not effective at all. After looking to the backend setting, you will understand why. We talk a lot about the three example things which will confuse people when it comes to bandwidth profile. Let's start the real thing for this video, which is let's check the backend settings. I am going to use this type of screen layout for the backend setting explanation. I will show you the network controller and the diagram. Then in the lower part of the window, I will open two sessions. Both are SSH to the same number 2 access point. The reason I want to show you two SSH sessions is because sometimes I want to compare the results for two different commands side by side. Let me SSH into the AP number 2. And in this part of the video, I'm going to talk a lot about the Linux traffic control. Many concepts such as queuing disciplines, classes, filters. If you don't know what I'm talking about, I strongly recommend you watch one of my previous videos for smart queues, because Ubiquiti uses the same Linux traffic control functionality to implement smart queues and the bandwidth profiles. So they are based on the same technology from Linux. In this video, I will not explain the basic concepts. I will directly dig into the details. There is one thing I need to mention here. This video already involves a lot of technical details. To make the scenario simpler, I am going to disable the wireless meshing feature. By default, it's enabled, but it will introduce some unnecessary complexity. So I will disable that. Maybe in the future, I will have some separate videos explaining how the wireless meshing is implemented in the backend. But in this video, let's not worry about this more advanced feature. Let me disable it. Finally, we can go to the system to show the technical details. I already connected the two computers to different APs. Let's go to the AP2 to see the current interface situation. I'm going to show the links. You can see by default, the system already comes with 26 interfaces. Yes, you see the familiar arrow, and the S0 is for the RJ45 part on the AP. For most others, they don't really look familiar to most people, and most of them are even showing down status, but some of them do show active. We cannot easily tell which one is for the one we use, but we are pretty sure the SSID must be associated with some wireless interfaces. How do we find it out? There's another command, it's iwconfig. You may be familiar with ifconfig. The iwconfig is specifically for wireless interfaces. This is much cleaner. As you can see, currently there are only two active wireless interfaces, and they both have the SSID Z11. Y2, I enabled both frequencies, 2.4 GHz and 5 GHz. That's why you see 2. And in fact, by the naming convention, RA is for 2.4 GHz, RAI for 5 GHz. Now I only have one SSID enabled, so it starts with 0. If I enable other SSID, you will see the 1, 2, 3 correspondingly. RAI 0 is for the one we are using now for 5 GHz Z11 SSID. Now we know the interface. In the left side, let me clear screen and run the command TC, which is for Linux traffic control. I want to show the queuing disciplines. Device, which is the one we just found out, RAI 0. This is the queuing disciplines. You can find some familiar names if you watched my previous video about smart queues. It's using HTB under it. It's using the fair queue Caudal queuing discipline as well. I'm going to run TC command, but show the class information for the same device, RAI 0. Now we have the queuing disciplines and the corresponding classes side by side. I won't spend time explaining all the details. If you are interested, watch my previous smart queues video. Just for your convenience, based on the information, I already prepared a class tree so that you can easily understand what's going on here. The naming convention for the class and the queuing discipline, it has the two-part naming separated by a colon. The first part is called major number. The second part is called minor number. If you see something which doesn't have the minor number, which means it's for queuing discipline. If you see both major and minor number, it's for class. Normally for a class, the major number indicate the queuing discipline ID. As long as you understand that part, you can also easily draw the class diagram in this way as well. From the title, you can see it's only for download. It's very important, but we need to talk about that later. For now, let's just look at the tree. So the root is a HTB, and then it has a class, and this class, if you check the information here, it says CEIL 2.4 GHz. This is for ceiling, which means the upper limit. So for the root class, the upper limit much more than the limit we set. Why? Because we are talking about a Wi-Fi AP based on the hardware restriction. It has different upper limit for, let's say, 10 gigabit switch or 1 gigabit switch or an AP. For this particular AP, it's 2.4 gigahertz. Okay, moving on. Yes, it's split it to two HTTP class, and in fact, this is called root class. This is called either inner class or leaf class. They are associated with their own disciplines as well. So from the legend, you can see blue color means queuing discipline, green color means class. You don't need to worry about this part because they have nothing to do with this video. Just look at this right branch. So far, you still don't see the upper limit which we set, 11 megabits. Once you are here, all of a sudden you see this particular class. Let me highlight it in the SSH part. See, the ceiling value is 11 megabit. That's exactly what we set in the network controller in the particular bandwidth profile. You don't see the most right branch yet. We will talk about that later. Now this particular part, the subtree, is the one you are most interested in because that's exactly what we set for the download limit. This is the class tree. So basically the traffic control, the way it works is for each network packet, the kernel need to understand, okay, how I do the limitation, how I want to do the shaping. By different class filters, the system will identify the corresponding correct class for that particular packet, then apply all the restriction. We will talk about how the system identify the network packets and apply the correct download limit later. So now based on these two command output, I draw this tree information. This is only for download. If you look at the complete information in the SSH part, you don't see 1.1 megabit, which is the upload limit. Why is that? That will lead to another very important concept, egress and ingress. Let me show you a simple slide I prepared. Sometimes it's a little bit confusing because the direction all depends on from where you look at it. In the middle, you have an AP. You use it to connect to internet, and your wireless device is connected to the AP, right? For the AP, of course, it has the Wi-Fi signal, but it needs a RJ45 Ethernet port to connect to your router and then connect to internet. In fact, we are talking about two interfaces for the same AP already. If you look from your Wi-Fi client perspective, when you want to upload something, your traffic is outgoing. When you download something, your traffic is incoming. But if you look at it from the AP perspective, when your client uploads something, the AP is receiving something, right? Then to the AP is incoming, or to use another word, ingress. When your client is downloading, to the AP, it's sending data. To put it in another word, egress. You see the difference, right? It's just completely the other way, or depending on how you look at it. To make it even more difficult to understand, when the traffic comes to the Ethernet port, it comes outgoing to the internet. If you look at from the RJ45 port perspective, when your client is uploading something, your AP is receiving something, but the RJ45 need to send the packets out to the internet. When your client is uploading to the Ethernet port, it's egress. For download, it's the same situation. From the RJ45 Ethernet port perspective, it's incoming traffic, it's ingress. I talked about the three different ways to look at the same packet. The important thing is there's a very, very important concept in Linux traffic control, which is it only controls the egress traffic. It cannot control the ingress traffic. It makes sense because for egress, the device itself has the control. It can put all the traffics in whatever queues and decide when to send it, how to send it, right? But for incoming traffics, the packets are sent by other devices outside of the control of the operating system for this AP. It cannot really control the incoming traffic. That's why the traffic control doesn't apply to incoming. But there's a way to work around it. If you watch my smart queues video, you can see for the smart queues for Ethernet ports, you can use a virtual interface, and then you can set the limitation in the virtual interface. But here for the bandwidth profile for AP, it doesn't work that way. The way it works is we will see it in the system. Let me run another command, which is bridge control, BRCTL. Let me show the current bridge. Even we are talking about the AP, internally it has a bridge, and the bridge name is BR0. It has 3 interfaces involved at this moment. Why 3? As we discussed already, RAI0 and RA0 are for the 2 different frequencies of Wi-Fi signals, and the Ethernet 0 is for all the packets which need to be communicated outside of the AP. So in total, you have 3 interfaces. We run the TC class command, show the device RAI0, right? Let's run the similar command, but the device is Ethernet 0. Let's see what will happen. See this particular class, it says ceiling 1.1 megabits. That's exactly what we set for the upload speed limit. If you check this egress versus ingress diagram, you may understand it better. For upload, from the Ethernet 0 perspective, it's egress. So the Linux traffic control can control it. When you try to set the download limit from the AP, the wireless interface perspective, it's egress. So the system can control it. That's why for download limit, you can see it from the RAI0 interface, but for upload, you can only see it in the Ethernet 0 port. Because of the way it works here, the same implementation cannot apply to wired client, because for wired client, you don't have a wireless AP interface. That's why the same approach doesn't work for wired client. We already answered the first problem we discussed in the beginning of the video. This slide is for the download limit and is for device RAI0. Similarly, I prepared the other one. It's for upload, but this time the device is for Ethernet 0 part. They look almost exactly the same. The only difference is, okay, for most of the classes, the upper limit is 1 gigabit because we are talking about Ethernet part instead of the Wi-Fi. So for this particular AP, the Ethernet part has the 1 gigabit upper limit, right? It makes sense. And then the other difference is for this particular class, for the upload limit is 1.1 megabits. But the tree structure for the Ethernet 0 looks identical for the RAI0. Now we know the class structures for the 2 interfaces when we only have one Wi-Fi client connected. Let me connect the second one. Okay, I connected the other Mac. So now we have 2 Macs on the same AP, and let's see what's the current situation for queuing discipline and for classes. Let me run the exact same command for the interface RAI0. Okay, this is the queuing discipline. This is for the classes. From the left side for queuing disciplines, the only new thing is the very last queuing discipline. Originally, we only have the 1008. Now we have 1009. In the right side, let's see what's the R009's class. Speed limit, 11 megabits. Why? Because we didn't customize the other Mac's bandwidth profile. It has the default one for the AP, which is also 11 megabits. So that's why for these 2 classes, you see the same upper limit, 11 megabits. Go back to the tree structure. That's why in the right side, you see another subtree, which look exactly the same as this one. The only difference is the class ID, 1008, 1009. Now we understand the system will dynamically add or remove the subtrees based on your connected device. For the 2 Macs, I didn't customize their bandwidth profile, so they defer to the AP's bandwidth profile. But we see 2 different classes. That explains the second problem we mentioned in the beginning of the video, which is the bandwidth profile only applies to client instead of the whole AP. It doesn't matter whether in the client you customize the bandwidth profile or not. In the end, the system will create a new subtree and create a new class with the corresponding upper limit. So that's how the system maintains this tree during runtime. That answered the second question. But you may ask, okay, now we have two different classes and they have the same limit. How the system decide, okay, for the Mac 1, the traffic, the packets for Mac 1, it will go to which class, which queues, right? That's something we need to answer. And to understand that, we have to understand some backend system settings. So let me go to the TMP folder. You can see there's a running config file and it has the configurations for the AP during runtime. So let me display the content of the file. We can directly jump to the part which we are interested. Let me search for VAP. See this part, QoS, VAP1, VAP2. And what is VAP1? The device name is RA0 and the uplink is for Ethernet 0. What we are using now is the RAI0, which has the ID 2. The 2 number is very important. What's VAP? Virtual AP. So you only have one physical access point, but you can define multiple SSIDs, and for each SSID you can see whether it supports 2.4 or 5 or both. That's why you have virtual APs, and for each VAP it has its own unique ID. Let me go to the MAC concept. See the Mark 1, 2, 3. In this video, we are only interested in Mark 2 and Mark 3. We are talking about some special bytes in your network packet, and the system can give it some particular meaningful value in the flow for your traffic. System can use those particular values to do some special operations. The mark is only dealt with inside Linux kernel. To put it the other way, if you use, let's say, network packets capturing tool, for example, Wireshark, you will not see the mark value because they are only available inside the Linux kernel. And let's read the Mark 2 and the Mark 3 a little bit first. The Mark 2 says, okay, we are going to use the Ubiquiti's special bytes. It contains 5 bits. The name is your VAP ID. Remember what's our VAP ID? Is 2. And then shift 11 means, okay, you have value 2, but you cannot directly use it. You need to shift it to the left, shift 11 bits. We will talk about the details later. And then let's check the third mark. It's the same Ubiquiti's special location, and the name is associate ID. It has 11 bits, and you don't need to shift it. What's this for? It is for your particular device. So for each device, for each Wi-Fi device, the system will give it a ID, and then this ID plus the VAP ID will determine how the system put your packets into which queue. Now we have to show another important concept in Linux traffic control, which is called filter. Let me show filter for the device RAI0 and check this subtree. It is under the class 100. I'm only interested in this subtree, so I will put a parent 100 here. The filter decides for each packet which class the system will use to process that packet. See here, it only has one filter, but we are talking about 2 Wi-Fi classes. Here in the tree, you see 2 separate subtrees. How the one filter can support 2, we have to look into the details. Filter for all protocol, and then basically it's just a sequential number. If you are familiar with firewall, you know for your firewall rules, it has numbers. Numbers basically represent the priority, right? The system will execute the rules by its sequential number. So basically this number means the same thing. FW means firewall. The system will look into the special mark, which is called FW mark. and then to match to see whether your packet has this special value 1000. If it does, it will say, okay, your packet match the class. I will put your packet here, and see here it will check the Ubiquiti's special bytes. Once it match, it will put to this class. TC filter add FW help. This help information is very simple, but it's well written. You can understand the filter, how it works. I'm showing you two different processes, but basically the second process is just the reversed way of the first process. The first process is how the system generates the mark. And the second process is how the system interprets the mark so that the system knows how to put a particular network packet to the correct classes. Let's check the left side process first. Let's assume this is the value in the Ubiquiti's bytes in the packet. Initially, of course, it's all 0, right? By the way, I'm showing you the binary value just for easier understanding. We need to do a bitwise OR operation against what value? The 11-bit client ID. Based on the Linux traffic control classes and filters, on paper, I know this is the initial device ID for my Mac, but I don't have time to figure out how the system decide, okay, for my particular Mac, it is this value. Let's assume, okay, this is my device ID. Then we will do a OR operation. We come up with this value, right? The calculation is not done yet. It will continue. It will use this value and then do another OR operation. This time, we will OR the virtual AP ID from the system configuration for our particular RAI0. The ID is 2, right? Then if you convert 2 to binary value, it's this red part, 00010. Then you need to shift it left, shift it 11 bits. Then you come up with this value. Why 11 bits? That's defined in another part of the configuration file. For the VAP ID, you need to shift 11 bits. We shift it, we come up with this value, then we do a OR operation, get the final FW mark, which is this value. And then your packet will be associated with this value, and then the Linux kernel will use this FW mark in different steps of the flow. Okay, let's assume you already have the FW mark in your packet. Your AP received such a packet. How it knows how to put it to the correct traffic control queuing disciplines and classes. Let's see how the filter works. Okay, we get this value from given network packet, which comes from my Mac. Then we will do a AND operation, AND with this value. Where this red number come from? From our filter. See here, it has this 0xF800 value. It is the hexadecimal value. Just convert it to binary, you will come up with this number. You need to do a AND operation. In fact, just think about the other way. The so-called AND operation with number, simply it means I don't care about the remaining 11 bits. I only care about the first 5 bits. That's what this AND operation really means. We get this number. So see the right 11 bits, they are all cleared to 0. If you convert this binary number to hexadecimal, that's exactly 0x1000. Is this number familiar? Yes. It is in another part of the filter, the handle. As long as your mark match this handle, that means this filter match. I have a green tick here. That means your packet match the handle. Then the system will proceed to decide where to put your packet. So you have this FW mark. It will do a further operation. This time is sorry, there's something wrong here. This time is also AND operation. So basically you need to AND this value with this value. Where this 0x7ff come from the same filter. See this number? It's called a mask. So basically you need to do a bitwise AND operation with this number. Then you come up with this number. Now we already used all the 3 special numbers in the filters. You have this number. Again, the process is not done yet. The very last step, you need to do another operation. but it's not and, it's not or, it's add operation. You need to add this number with the class minor number. Where is the class minor number? It's here. In the filter, you can find a class ID, right? As I mentioned, before the colon is major number, after the colon is minor number. So that's where the 1000 come from. You do a add operation. You come up with this number. This number is in binary format, but if you convert it to hexadecimal, it's 1008. Is it familiar? It is exactly for our bandwidth profile. It has the 11 megabits download limit. So that's why by using this very simple filter, the system can dynamically decide which subtree to put your packet to. The system doesn't need to introduce a new filter if you have a new device added. No, just one filter will support many devices. As the last part, let's discuss why if I move the PC to the second AP, all of a sudden the bandwidth profiles stop working, which is the third problems we mentioned in the beginning of the video. Unfortunately, I don't have hard evidence to prove my understanding is correct. It's just what I guess. So think about it. I use this Mac. I set the download limit and I connect the Mac to the PC, right? So the download for this Mac means the upload for this PC. But from the Linux traffic control perspective, for this Mac, number one, to limit its download speed, yes, there's a queuing discipline and a corresponding class for it. It's doable. But when the traffic goes to the PC, yes, the PC will have the upload limit implemented in the Ethernet 0 port. But remember, both devices are in the same AP. So the traffic doesn't need to go through the RJ45 port, which means the Ethernet 0 upper limit for the upload speed for PC doesn't work. So that's why for download, the bandwidth settings here and here don't work together. That's why in the end, it doesn't limit the download. If you talk about upload, the similar case. The upload for the Mac will be the download for the PC, and the upload limit for the Mac is implemented in the Ethernet 0 port. But because both PC and the Mac, they are inside the same AP, the traffic doesn't need to go through the Ethernet 0 port. That's why the bandwidth profile doesn't work. Okay, this is just my guess. If you know better answer, let me know please in the comments area. Okay, after the very detailed technical discussions, I hope you somehow understand how the bandwidth profile is implemented inside Ubiquiti's Wi-Fi access points, and I hope it answers some of your confusions about bandwidth profiles. Okay, thanks for watching.